Hello everybody. In this lecture series I'm talking you through how I would apply the chain ladder method in practice to a few example datasets. This covers selecting link ratios, fitting curves and checking results. And throughout I'm highlighting where the chain ladder method is or isn't appropriate. In this third and final video in the series I'm going to explain the various ways I go about checking that my selected ultimates are reliable, as well as understanding where they might not be, as the chain ladder method was not well suited to the particular features of the segment being modelled. Both these assessments are important in order to justify and document your modelling. So let's start. At this point, we've used the chain ladder model to complete our y equals m times x equation. As a reminder, the x values represent the latest development data for each origin period, and we've used the chain ladder model to set the m values which derive the y values, the ultimate claims, for each origin period. We've done this through selecting link ratios and fitting curves, as covered in the previous two videos in this series. However, we're not done yet. We need to consider the results to ensure that we're happy with our model, and equally crucially, where we're not. Let's start this process by considering a summary of the results of an example model. So this is showing me my x and y values for each origin period. Latest paid being my x values in this example. It also shows me the difference between x and y, the claims reserve in this example. And finally it breaks down the claims reserve into two separate parts, the triangle reserve and the tail reserve. The triangle reserve uses the selected link ratios to take each origin year from the latest development point up to the end of the triangle. The tail reserve is the final step from the end of the triangle to ultimate. And obviously where we have no tail factor, then we have no tail reserve. We discussed how to set tail factors in detail in the last video. There are a variety of checks we can now do on this table of absolute numbers. Firstly, the triangle reserve must be 0 for the oldest origin period. If you're doing the chain ladder method on a spreadsheet or a self-built tool, then this is a quick error check on your model. Next, we can consider the ratio of triangle to tail reserve in totality. Models with a high proportion of tail reserve are generally more concerning to the reviewer. Not necessarily wrong, but perhaps indicative that we've lacked historical data for our modelling purposes and that the chain ladder method might struggle to provide a reliable result. I generally expect the total reserve, y minus x, to be increasing through the origin periods. This is because over time more and more claims will have completed their journey through the policy life cycle, and so older origin periods should be closer to ultimate. A distortion in this trend could be driven by a reduction in the size of the book over time, or it might indicate an issue in the modelling process. If so, we need to reassess our ratio and curve selections. I generally expect the value of the ultimate y to be broadly consistent across origin periods. Now obviously an account could be growing or contracting in size, or profitability, or inflation might be high, which would lead to increasing or decreasing ultimate values over time. So it's not a perfect check. However, if I see very small values for ultimates in the back years and very high values in recent years, then I'm going to be concerned over the material change in makeup of the book, which might invalidate the chain ladder method due to heterogeneity. It might also indicate that we have insufficient historical data to calibrate our model, again invalidating the chain ladder method. In this example, I'm modelling a triangle of paid data, and I do strongly recommend you model paid as well as incurred data to get two views of the likely ultimate claims in each segment. And in this case, when you're modelling paid, be careful if you have a negative total reserve for any origin period. This means we're expecting to get more money back from customers than we pay out to them in future on that origin period. This could happen. Think of the late recoveries that can happen on a war account, for instance, but generally it doesn't, so it's probably indicating a modelling issue. Note that if we were modelling incurred data rather than paid, then getting a negative reserve is less unlikely, as we might simply be reflecting prudence in the setting of case estimates by the claims department. Although again, we should ensure this is a genuine feature and not just a flaw in our modelling process. So there are quite a few checks we can do just by eyeballing this table of absolute numbers. However, as usual, a picture can paint 1,000 words, and so we should think about what graphs we can use to break down this information into a more digestible exhibit. We've also just been looking at absolute numbers, and it can be hard to put these pure amounts into context. So let's also consider any exposure measures we could use to get that context. The obvious measure to use would be earned premiums, but we should also be trying to source and use other measures such as policy count, claim numbers, and in fact any relevant measure of the risk undertaken that we have accumulated during the preparation stage of our modelling process. This first exhibit compares the ultimate claims derived from my chain ladder model against the equivalent earned premium for each origin period. This ratio is known as the loss or claims ratio and is very commonly used. I can very quickly see that the earned premiums, the grey columns, look pretty constant from origin period to origin period. So we're not seeing any big growth or contraction in this book. I can also see that the loss ratio, the blue line, is very constant across origin periods with no clear trend. The loss ratio itself is about 70%, so paying out 70 pence for every pound of premium. Remember that insurers need to make a profit to be sustainable businesses, so we would expect loss ratios not to regularly exceed a profitable level, i.e. they should be below 100%, probably by a fair bit to allow for expenses and commission as well. Given the stability of loss ratios in this example, it looks like a short tail book that probably requires a low level of capital and hence profitability. More volatile lines of business may require lower average loss ratios to give a sufficient return on capital employed, so do be aware of this when judging profitability. And if the modelled loss ratios on average don't look sensible, we should check that we haven't miscalibrated our chain ladder model. And even if we're satisfied on that point, we should be prepared to defend our position against underwriters who will be financially impacted by this conclusion, positively or negatively. Generally, we might expect there to be some consistency over time in loss ratios, and it's very useful to put the more uncertain, i.e. recent years' performance into context. Do they look very profitable or unprofitable? Do we believe it? We can see here that the recent origin periods look very much in line with the historical trend, which is good. We may have heard discussions of price wars or rating action when we engage with underwriters, and the underwriting cycle is a very real thing in most insurance classes, so variability over time can be normal as capital flows into profitable areas and drives down premiums, as well as vice versa. Ultimately, it's a subjective call, but we should at least be cognizant of these trends and be comfortable that they are reasonable and defendable. This exhibit is not causing me any concerns, so this chain ladder model would get a strong pass on this particular check from me. Let's look at some more challenging examples. This one is much more challenging. What we're looking at now is a check on a claim number model, either closed or reported, including or excluding nils. Make sure you know which when you do this for real. Where we are comparing the ultimate claim numbers against the earned policy counts, and hence showing the frequency of claims by origin period. Well, on the plus side, the exposure looks reasonable over origin periods, which is good. However, we do not have stable claim frequency over time, which is concerning. Either this is a small class, a long tail one, or one which is subject to strong external factors driving frequency. I need to check back to my preparatory investigations to understand as well as being sure my modelling was well founded. We do have claim frequency for more recent years, looking about in line with the historical average, circa 20-25%, so 1 in 4 or 5 policies having a claim. Although I am concerned by the high level of frequency seen in 2018, I want to understand how developed the claim counts are in that 28 origin year before making a call here. So this exhibit is not a definitive pass or a fail for me, but one which requires more investigation. This one rings alarm bells immediately to me. What we're looking at now is a check on a claim amounts model, either paid or incurred, where we are comparing the ultimate claim amounts against the ultimate claim numbers, hence showing the average cost of claims by origin period. Now we do have to bear in mind that, as we've just seen, the ultimate numbers value is itself an estimate, and so this test can be biased by a poor ultimate claim number projection. However, we should generally find that claim numbers are more easily modelled than claim amounts, as we could quickly know if a claim has happened or not, but it can take a long time to complete the claim assessment and settlement stage of the policy lifecycle, which is required to assess claim amounts. In this case, I can see that my claim numbers, the grey bars, look pretty reliable, with broadly equal numbers of claims in each origin year. What looks a lot less good is the average cost of these claims. There appears to have been a step up in 2019, leading to a 50% jump in average cost. Now this is where we check on our discussions with claims and underwriting. Have we materially changed the type of business we are writing that would lead to such a step change? More likely, one or two scenarios has happened. Firstly, the claim department has recently changed their approach to setting case estimates, and we're just projecting forward that without thinking, almost certainly leading to bias. Or secondly, the claim development is quite long-tailed, and our projection of the more recent origin years is not reliable. In this case, we may need to use a different method, or fix the average cost in those recent years. We'll do some checks shortly to help us see what's happening better. This last exhibit of this type goes back to comparing the ultimate claims derived from my chain ladder model against the equivalent earned premium for each origin period to show the loss ratio trend. And that trend is very concerning. We can see that the earned premiums, the grey columns, broadly doubled over the period shown. Meanwhile, the loss ratios, the blue line, have quadrupled and are now looking very unprofitable, heading over 100%. Again, we need to check back to our preparatory work. Is this growth into new areas which develop differently? If so, do we need to split this segment down into more homogeneous sections? Should we be using averages of more recent historical link ratios to reflect this changing trend? Are any of these origin periods mature and hence the trend is real? Or is this all based on our projection? If it's our projection driving this, then I'd be going back to reassess whether my ratio and curve selections were truly best estimate. In any case, this looks like either a clear fail or something I need to communicate to underwriters quickly, as remedial action is required if this is a real trend. Let's now look at another check on our modelling, the All Origins development chart. This exhibit is showing the development data for each origin period as a percentage of the ultimate set in the chain ladder model for those origin periods. The latest development percentage point for each origin period is always equal to our 1/m chart we looked at in a previous video, but all prior development is unconstrained. By looking at such an all origins chart, we can quickly tell two things. Firstly, whether the historic data is trending towards the ultimate or not. In this example, I'd say that it is, with the development seeming to tail off after about 9 periods. This has given me comfort around the tail factor setting process, and also that we have sufficient historical data to successfully calibrate the chain ladder model. Secondly, I can quickly tell whether the claim development by origin period is consistent or not. The whole point of our modelling was to detect the true but unknown development pattern, so this enables me to quickly see if one is apparent. In this example, the data does all look quite tight to the 1/m development pattern we set in the model. With each origin year's development closely aligned, it gives me confidence in using the chain ladder method on this dataset, as there seems to be little noise around the true underlying development pattern for this segment. It's also interesting to note that despite the paid claims being quite long-tailed, for example only 25% developed after 1 period, they are so consistent that we may be able to rely on this estimate more than where we have a shorter-tailed but inconsistently developing segment. Let's look at another example. This all origins chart is posing us more problems than the last one. On the plus side, we can see that the data gets stable later on, and that this development does seem to be trending towards our ultimate. However, the development is very unstable in the first couple of development periods and only settles down later. In this example, I would want to strongly check the results for the more recent origin periods by comparing against exposure, for example looking at loss ratios, as well as considering other reserving methods which may be less reliant on development and hence more reliable. However, the results for the older origin periods derived from this chain ladder model should be fine to use. This all origins chart is setting off alarm bells for me again. It's clear that our data is quite stable but also quite long-tailed. We clearly don't have enough historic data to enable all claims to have completed their journey through the policy lifecycle. We can see claims development still being strong by the end of the triangle, and we've not applied a tail factor at all. In this case, we need to go back and reassess our curve fitting to get reasonable results from our model. On the plus side, the ratios work looks good. We're going to have to make a decision later about whether we can rely on the projection for more recent periods, given how far from ultimate the claims are, even after 3 or 4 development periods. This all origins chart looks horrendous. The historical data is incredibly volatile, especially at first, but also running right through into the tail. The true but unknown development pattern is really not apparent to me. It may be the case that we need to consider other reserving methods, as the chain ladder method is going to struggle to find the true development pattern from all the noise we're seeing in the data. Or maybe we need to think again about our segmentation and get more homogeneous data to model. Perhaps this class is very small and we need to use a benchmark, as there's just not enough data in this segment for any method to work at all. Note that this should only be the case for the smaller segments. If we're using benchmarks for our largest segments, then something needs to change, or we're working for a very new insurance company. The last case we might see is where the data looks consistent but is tailing off, say at 80 to 90% of the ultimate set. We could get this kind of scenario where we picked a prudent tail factor. At that point we would naturally go back to our curve fitting selections and pick something shorter tailed. Remember, we're interested in the potential range of results we can get, so it may make sense to save down such an ultimate as a prudent marker, as it's well calibrated but doesn't look quite right. Generally speaking, if I come to review your work and you've just saved down one incurred chain ladder model, then you're sending a strong message that this is an easy class and you've nailed the modelling. If you're not so confident, and we rarely are, then try a few different calibrations and save them all down. The range of results will be really helpful in understanding how sensitive this segment is to modelling judgments. Also remember that we're going to be modelling multiple datasets, paid and incurred for example, so things may look fine here compared to the data modelled, but we still need to pass a number of acid tests against unmodelled data before we're satisfied with this model and the final results for this segment. This will be covered in the next lecture in the series. The final test of our model is to compare the actual development data for each origin period against the expected data for that same development period, as derived from our chain ladder model. Just as we can use the selected link ratios to predict the future, multiplying forward from the latest development point, we can also use them to tell us what would have been expected in the past too, by applying the selected link ratios from the latest development point back in time. So in this exhibit I've got my actual data in blue, and I'm comparing it against expected data in orange. Again, the expected development pattern is equal to our 1 over m chart we looked at in a previous video. Now there are two things I'm appraising here. Firstly, is there a good fit between the actual and expected development, the blue and the orange lines? For this origin period I'd say emphatically yes, as it's almost identical. We don't normally get perfect alignment here, but we should be seeing a broad mirroring of shape. We need to flip through lots of these single origin period charts to get comfortable that historical patterns are stable and that our modelling is replicating them well. Secondly, we can again check whether the actual data looks like it's trending towards our ultimate. We did this with the all origins chart, but we can often spot more detail and concerns when we consider each individual origin period in isolation. This particular origin year looks fine, but again we should flip through a number of origin periods charts to form our final view here. Let's look at a different model with more issues. This exhibit is showing a strong divergence between the actual and the expected development pattern. This is immediately concerning, although I'd need to look at more individual origin year charts to fully form my view of what the problem is. Perhaps it's just a single outlying year, in which case I might accept that and move on. However, it could be part of a changing trend in claim development over time, caused by internal or external influences on the policy lifecycle. We should check back to our preparatory work to see if this is the case, and again reflect on segmentation and our modelling choices. Or it might just be indicative of generally unstable claim development in this class, with each origin period developing erratically. In this situation, we might need to consider using a different reserving method. The orange expected development profile looks like it's missing a tail factor here, and hence we have an optimistic model. But for this particular origin year, the actual development looks like it is trending below the selected ultimate. Overall, I'm not feeling confident in the projection of the 2016 origin year from this method. I need to feel better about the other origin year before I'd consider that this method has passed this test. So let's remind ourselves of the key steps around results appraisal that we've covered in this video. We have 4 key checks we can perform to appraise our results, and we should also be on high alert for where the chain ladder model is not reliable and we may need to use another reserving method. Let's step through these 4 checks in a little more detail. When we look at a summary of the absolute results of our chain ladder model, we can do 4 different checks. Check 1 is to look for obvious errors. Have we built the calculation in a spreadsheet and managed to get a triangle reserve on the oldest origin period, for example? Are we modelling paid claims and getting a negative reserve, i.e. expecting our customers to pay us money in future? Do remember though that negative IBNR is acceptable when modelling incurred claims. Next, we can compare the ratio of our tail and triangle reserves. Too high a tail reserve might indicate a lack of historical data, which might indicate the chain ladder method is not best placed to reserve this segment. Then we can check that the total reserves increase as we compare newer to older origin periods. Naturally, growth or contraction and other factors can alter this, but it's a good simple check to apply generally. Lastly, are the absolute ultimate values broadly consistent over origin periods? Be particularly worried if there are small ultimates in the older years, which we'd normally rely on to calibrate our model, and even more worried if that's accompanied by large ultimates in the recent years. If we got good data and done our preparatory work well, then we should have a range of exposure measures we can now use to standardise the absolute ultimates and make comparison across origin periods more informative. We've got another 5 checks we can apply to these standardised results. Firstly, we need to check that our exposure measure is consistent over origin periods. Remember that some exposure measures, such as ultimate claim numbers, may themselves be uncertain, and we can also get distortions from business growth or changes in mix. We may decide that some exposure measures are not reliable enough to use for this segment. Next, we want to check for consistency in our standardised results over origin periods. Can we justify the movements we see, or is there a lot of volatility, which might diminish our trust in our chain ladder model? We should be able to explain or justify what we see here. Then we can see that the overall level of the standardised result is reasonable. When we look at loss ratios, we know that insurers need to make a profit, but we also know that insurance is very competitive. So we should be sure that we trust our modelling when we project exceptionally good or bad loss ratio performance, as it will get a lot of scrutiny when we present to underwriters and management. We should focus in on the standardised result for the more recent origin periods, particularly those which we've noted have a high M value, i.e. are not very well developed. We may need to reassess our calibration to get a more reasonable result, or we may decide that the chain ladder method is not appropriate to use for those immature years. Lastly, we should pay attention to any trends in the standardised results. Is frequency shooting up, or claims inflation running wild, or loss ratios heading south? All these insights will be valuable to feedback to underwriters and management so that remedial action can be taken quickly. Comparing the development of the historical data as a percentage of our selected ultimate for each origin year gives us another 4 checks on our results. Firstly, we can quickly see if the historical development looks like it is trending to ultimate. If not, and say all the development is tailing off at 75% rather than 100% of ultimate, then we probably need to reassess our model calibration. In that situation, we probably have too long a tail factor. In others, we may need to add a tail factor. Next, we can see if the historical development looks consistent over origin periods. If not, it may well indicate a change in mix over time, which invalidates our assumption that historical development is predictive of future development. So we might need to reassess our segmentation or use a different method. We can look at the model development percentage, our 1 over m values, to see where the model is likely to be reliable or not. I have a rule of thumb that origin periods where development is less than 50% of ultimate may not be reliably modelled using chain ladder. However, you can get stable accounts where you can go lower and unstable accounts where a higher threshold is required. Lastly, do we get reasonably consistent development, or do we get a huge spread of potential development percentages for many development periods? If the latter, then we might decide that the chain ladder method is not appropriate for this segment. final set of checks is to consider the actual historic data against that expected from our model for individual origin periods. Generally, we need to flick through each of the origin periods to get comfortable with our model results. What we're looking for is a good fit between actual and expected development. 1 or 2 outlying origin periods might be fine, but we may also spot a changing trend requiring recalibration of our model, or possibly a need for improved segmentation. Next, does the historical development look like it's trending to ultimate? Again, 1 or 2 outliers or a balance of origin periods looking slightly optimistic or pessimistic might be fine, but if not, we probably need to reassess our ratio and curve fitting selections. Lastly, we should be able to clearly see which origin periods look reliably modelled and which look sufficiently immature or erratic that the chain ladder method will not be a useful estimate. So hopefully you are now much more clear on how to check that your chain ladder method is reliably calibrated, and also when it's not. This step of reasonableness checking is often missed by junior actuaries who are so busy doing the work that they don't step back and ensure what they've done is correct or justifiable. As a reviewer, when I come to a class fresh, it's often incredibly obvious that the modelling is not optimal, and it immediately makes me nervous of whether the modeller has really thought about what they're doing. Remember, I can write a macro or some Python code to turn the handle on this modelling, so you need to think about what you're doing and not just bash out models without thinking. If you go through the various steps I've outlined in the 3 videos in this practical modelling lecture, then you should end up with chain ladder models that are as reliable as possible. Now remember, we will have modelled a variety of data sources: closed, reported, average cost, paid, incurred, etc. Probably multiple times to test our assumption choices. And we need to bring this all together into a predicted ultimate for each origin period for that segment, and all the others too. The next lecture will talk you through how I go about sifting through the various models to make those final selections, as well as when I decide that I need to find another method for certain origin periods, or whole segments, as none of my chain ladder model results are sufficiently reliable. You should be able to see the next video in this series on the left hand side here, so please click to move on to it now. As usual, please also like and subscribe to support these videos. Again, you should be able to see a small circle which you can click to subscribe. And do let me know your comments and feedback on these videos in the comments section below. Thank you.